Today we're doing like Q-learning, the fun stuff. The whole point of this semester was supposed to be Q-learning, right? So very generally, before we get into it, Q-learning is really cool because it's a way of having some agent in an environment, and like I'm an agent, for example, take some action, and you can reward certain actions and penalize other actions. So you can think of this as like a precursor, or maybe even the method you use to train like robotics or other like game AIs, of course, is what we want to talk about. But this is very applicable and cool, very, very general. But before we can get into Q-learning, it's a little bit important to talk about what our like goals are. So I have a lot of jargon in this meeting, and I'm going to try and break down the jargon. If you guys ever are confused at the jargon, please let me know so we can keep talking about that jargon. Because I think Q-learning is one of the most jargon-filled bits of machine learning, and it's, jargon's useful and all, but I think it's a huge barrier to entry. So if I confuse you with the jargon ever, please stop me. So we really want our agent to be able to take actions in an environment of some kind. We'll define like what actions are and what an environment is, but some robot in the world or some snake trying to eat an apple. These are your actions and environments. So before we can get into our Q-learning, I think it would be a disservice to not talk about this annoying jargon, Markov decision processes. It's like a very scary term, but it's not so complicated. First, we can break down the words itself. So decision process is like very human. This is the process you're making to make a decision, right? Nothing too crazy. So when you make a decision, you probably think about it. There's your process. So in the context of like a snake game where you want to go towards the apple and you're in this grid world, you might want to go up or down or left or right, right? So these are the actions you can take. But the actual decision process is this, should I go up, right? So you should be thinking, should I be going up? Should I be going down, et cetera? Then the Markov bit, I think, is a little bit scarier to tell people. In general, the Markov bit is saying that you have a current state, and the future state only depends on the action. And we're going to have a few examples of this to hopefully break it into a more human term. But very, very generally, we don't need past states to influence our future. And so like we can think of a lot of things as Markov decision processes, but we'll have to justify some of these. So I have these main properties set up for the decision process. These P and R are a little bit confusing. Luckily, we're going to eventually get rid of them. But to talk about these in detail, that was a weird way to say that. You have all of your states in like some set S, and then you have actions that you can take at your states, and then you have the chance that your probability, or the chance that your actions will resolve to a certain state. Right, so if I take one action, I might end up in this area, but I might end up in some other area, and we'll break into like human terms here soon. Don't worry. You also have the rewards. So maybe it was really good that I took this step, or maybe it wasn't. So having a number of what action is good is part of the Markov decision process. So I have this really silly slide to farm engagement with you all. The idea is I want you all to talk with your neighbor and see if you can realistically justify, do any of these fit Markov decision processes, or maybe they all don't. Maybe some of them do. I will give you all a hint that you can probably justify all of them, or maybe not all of them, but some of them is going both ways. So I want you to talk with someone around you right now to pause and ponder and think about, are these games Markov decision processes, or can you solve them using Markov decision processes? So take a moment, talk with someone.
Is definitely Markov decision process.
I don't know.
Join the group behind you here. You guys together.
Think the problem like
Depending on the.
so in a Markov decision process, you need a data. I don't know.
I think
You need a set of action.
Result data. Yeah.
And then I mean, that's basically it, and then.
Me?
And
I
yeah,
don't
and then.
know.
Okay, let's start with the simple one, the state.
I mean, there's
Markov decision process.
One
So it has a
state.
state, right? So state would be its position in regards to the next like step.
Like the next, like the next would be.
But hopefully,
Is that
and then.
I mean, like, it's very, so that's what matters.
Yeah.
Dead.
Like how. Yeah, because like you can calculate that, the, right, like the what happened. Without like getting the body, you know, more like that happens. Now the question is, what about
Oh, no, totally. That implies that,
No, whatever, like, I don't. You know how it's about like initial, you go up, and like at some point, even like everyone in your team wait for their. That's good point. And then like, I don't.
Okay, I think about half of you are now bored, so I think that's a good stopping point for this. I'm hopefully going to hear some answers. So maybe we can start with tic-tac-toe. Does anyone want to try and justify one way or the other with tic-tac-toe? Go ahead.
It's like your state, it's like the whole board, like image, and then it's like where you put your X or O depends on like where all the other X and O's.
Right, like you have access to every state like already right now, and all of your actions are pretty clear, I think, and like the probabilities of your actions are pretty guaranteed, so you know those, and your rewards of winning, I'd say it's pretty good. Yeah, I think this is only ever going to be a Markov decision process. I don't know if you can justify it any other way, but maybe you could. Does anyone have any ideas for Go Fish? This one's debatable, I think. Sorry, go ahead.
Let's go.
That was hopefully not a question I had to answer today. It's that game where where both you and your opponent have cards, and then if you have like sevens, you can be like, do you have any sevens? And then hopefully they'll give you all of their sevens, and then you make sets. I guess not everyone has played that game. I thought that was like a normal thing. If we don't know Go Fish, we can move on to the next example. But does anyone want to try and justify Go Fish? Maybe not. So you have an idea?
I mean, I guess if you ask people for their cards, you don't really have like a very defined maybe like transition model where it's like where your actions transition you from one state to another.
Yeah, it's not clear what the probabilities are, which I think is what you're getting at, which I think is sort of leaning towards it being not a Markov decision process. But I think another point is if you ask, do you have any sevens? That implies that you have sevens. And so an action you took sort of adds to the state of the game, which is confusing because now your new state doesn't contain that action, but you do depend on that previous action. So I would argue that this is not a Markov decision process. You could certainly turn it into one with however you frame the problem, like if you include those into your state. But I think with a, say, conservative view of Go Fish, you probably would call it not a Markov decision process. The cool things with some of these is that they're debatable, which was hopefully the point. Could anyone try and justify Uno? Want to try Uno?
I think it's not a Markov decision process because best case, let's say you like throw in like your best move, like let's say, I don't know, put in a +4. Chances are your opponent doesn't, or opponents don't have like a power card to put in. So they would end up like have to give in and like take in 4 cards. But worst case scenario is, let's say you put a +4, but then your opponent or opponents also has a power card. And then they also pull in their best move. So it can turn out that your move gets backfired. So I guess the probabilities, like, there could be a best case and worst case. It's kind of.
See, assuming you have the probabilities, this actually could be taken into account in a Markov decision process. So for example, if there's a really high chance of your move being good for you, expectations would like take that into account. But if it has a low chance of being really bad for you, expectations would also take that into account. It's like your reward function ideally would take into account.
Opponent's next moves.
That would be something to consider. Maybe you don't have access to the entire state. And I think that would be a good way to justify it not being an MDP, because when you put like a card down in the pile, maybe it becomes not part of the state. So then your probabilities change in a way that you don't know. I think you could justify this either way. You have something to add?
Like probabilities based on what the cards that have been put down are. Like, do you know, like, what's the probability that he has like +4 in his hand?
Right.
You know, wouldn't you be able to calculate that, like expected value?
If you include it in your state, you would. So I would say that depending on whether, I would say that if Uno is an MDP, that probably means that like all of the cards in the deck that you've put down are in the state. Otherwise, it would not be an MDP, I think is a fair way of saying it. It depends. And then last we have Snake. Does anyone want to try Snake? This bottom game here. Snake, I think, is a little bit more straightforward if anyone's brave, but want to try?
I think it's like similar to the technical thing. You have access to how many cards.
Yeah, you have access to the whole grid. You know where your apples are. Your actions are pretty much always clear. So yeah, I would say that this is only going to be an MDP. Maybe it wouldn't be if you had like a cloud over it, but obviously that's not part of Snake. So Wikipedia loves this graph. I don't know if I love it. What they're trying to get at here is that in this game, not a very fun game, but it's a game, you have 3 states, and you can take actions. Like from state 2, you can take action 0, and it has some chance of resolving back to state 2, but it also has some chance to resolve back to state 0. So the idea is that if you can model your game in some graph view like this, it's probably a Markov decision process. And one of the cool things here is that we have reward functions associated with our paths or our actions. So if your goal is to maximize your reward, you can try and solve this decision process, right? Now, this one I actually didn't solve in advance, and I think it's kind of hard to because of all of the numbers. But there's probably a path in here that's like optimal to take to try and maximize your reward. And I'm not going to justify that now because it'll probably take me a while. But maybe there exists a path or multiple paths in here that you should just try and like loop over and over again to get the maximum reward from. And this is the problem we're trying to solve. So we are trying to convert our games, or maybe the real world, into Markov decision processes so we can use our algorithms we're going to talk about today to solve them. So whenever someone says Markov, you should probably be thinking something like this. So this is, I believe this is the last slide I have for the jargon here. So yeah, so before I move on, is there any confusion about Markov decision processes? Because it sort of builds up a little bit, so I don't want to move on without anyone. All right, people claim to be with me, so I'll just believe you. Okay, so before we get into Q learning, I feel like I have to talk about value iteration. I'm not really going to talk about this, as I say in my little note here. If you really care about all these different machine learning algorithms, you should take a class. Unfortunately, we can't do this for you, but value iteration has a cool visual for you, and I want to show that to you. But the idea behind value iteration is that it's a model solution. So in MDP, you have like multiple solutions, right? There's many ways to solve these like graphs. Value iteration is one that requires the whole model, right? And what a model means is that it has these functions, like this part of your MDP, and it can use those to sort of simulate in its head what's going on in the world. So chess isn't a great example, but you can kind of think of it in terms of in your own head, you can simulate what this move is doing and what the effects have on the world. I say chess isn't a great example because it's like adversarial and there's like weird bits there, but just for simplicity's sake, you can simulate a chessboard in your head before you actually take the action and measure it, right? So the idea is something that is a model solution, right, takes in these functions. And as I said, it lets you simulate like a faked version of the chessboard, and it lets you plan ahead. So I have one example we're going to look at a little bit is a maze solving. Maze solving might not be the best way of saying it, but you can imagine that like this 0 here, like all these are the same maze, just with different iterations on them. This 0 here is our like end goal. So we can probably find some way to apply like a reward to each of these squares to discourage you from going to bad ones and to encourage you to go to good ones. So if you want to maximize your reward, or in this case, try and get the least negative number, you would probably follow these least negative numbers. And this is the rough idea behind value iteration. In reality, it's a little bit more than that, but this is something I encourage you to explore on your own. But I had this very pretty demo from Kaparthi, my beloved. The idea here is that we have, it doesn't show up on this board at all very well, but we have this end state, which is a reward of 1. We have a couple like weird spots, like reward of -1. I'm sorry for the really bad quality. I didn't realize it would show up this poorly. So all of these times you see this little r here, these are actually negative ones. So the idea is we're going to start up here, and we're going to try and evaluate this board in some way to encourage us to go to our end state here. So this is, I'm going to toggle value iteration. It's going to go really quickly. It's going to use all of the information that is given to us in the Markov decision process to sort of like propagate outwards. So now whenever we're in that like top left tile, we know that going right or down are both like pretty good actions. So now value iteration has done this process where every action is sort of assigned like a really good number. So that way we know which action to take in which state. So this is one way to solve the Markov decision process. We can go through and we can iterate over the board a couple of times and try to solve it by like propagating these rewards outwards. So this is a, sorry, go ahead.
Are there rewards calculated as like a pathfinding algorithms?
It's not that complicated. It's in code, you're basically just going over the board and like literally taking the rewards and appending them. We're going to talk about a little bit more how this works in Q-learning soon, and I'm going to hopefully put it on the board. But you can think of it as the terms of like this reward at the start of it, right? If I reset. Oh, that wasn't very clever of me. If I reset now, the reward right now is 0. Right? But we want it to probably be pretty high, right? Because there's no penalty for going here. So we probably want to like transfer some of this reward to the previous one. So we're going to use an equation that lets us like bring it over. And we're going to do that a bunch of times across the whole board. Yeah, that's a good way to think of it. So if I toggle it, you'll see that it like updates. It might even update again. So you see how it like flows out a couple times. It might have converged by now. That's still updating a little bit, but it's going to like loop over the whole state space a few times until you converge to like the optimal result. Okay, so this is like a simple way of solving the Markov decision process. This is nice and all, but it requires a bunch of information. And I'm not going to justify that right now because I'm not too interested in value iteration today. But if you guys have interest in this, the code I believe is actually provided if you scroll down. So if I highly recommend this website, this is a good one. But I'm going to go back to the Q-learning bit. So in this value iteration, we have access to like simulate the board, right? We have access to these simulator functions, and we know what the exact reward is going to be if we move between states. Which is crucial because maybe we don't always have really good info here. So what if we don't have access to P and R? Like what if in the Markov decision process, it's not clear what those are? Like if I am a human in the world and my goal is to make mac and cheese, it's maybe a little bit hard to know what the probabilities of each of my actions are Like if I stir a pot, like how am I going to know what the probability of like that noodle colliding with that other noodle is? We're going to get really complicated functions that we can't really model. But maybe we can still say they're a Markov decision process. It's just hard to model, right? So this is where Q-learning comes in, because it doesn't require those other two, right? So if we go back to our 4 like really important Markov decision bits, what if we were to just remove these bottom 2? Could we still functionally learn? And we can. This is what Q-learning seeks to do. So let's try and look at it a little bit. So before I move on, Q-learning only has access to the states that you're currently in and the actions you can take in that state, which is really nice because you can model like anything that way, right? You can model Pac-Man, you can model the real world, you can do whatever you want. Okay, so Q-learning. This is probably a weird way to put it, but Q-learning doesn't know like everything about the world. It's just trying to look at how your agent interacts with the world. So Q-learning doesn't actually solve what the world is. It doesn't know how to simulate a chessboard. It's just trying its best. It's guessing and checking. So what Q-learning instead seeks to do is try and find a way to reward actions. And the very rough idea is that we want to create some function that takes in the current state of, say, like a chessboard, of maybe the world, and then some action, like taking their enemy queen with a knight or something, and see what the expected reward is from them. And this expected reward is the immediate reward we get, and then like all future rewards, right? So it's basically like, are we going to win?
Like a long-term reward.
Yes, and I'm going to talk about that more soon. So you can think of this in a few different ways. We're going to first look at like a grid world, but you can also think of the Q function as just like some map or dictionary of state action pairs. So like some number, right? If that number's high, that's a good reward. If that number's low, the bad reward. Right, so this is like the more primitive look at Q learning, but eventually we'll build up the neural network approach. And if you have this Q function that can take in your current state and any action, what can you do with this? I'm going to see if I can make you do it, because it'll appear here in a moment. But can anyone try and take a guess of what we can do with this information? Like, how can we choose next actions if we have this Q function and it's like accurate? You have an idea?
The one with the that gives the max reward.
Yeah, exactly. So all we're going to do is run this Q function on every single input, right? Every single action, and take the max. So maybe a little bit more mathematically said, we could say we're going to take the argmax of the reward function. Have I lost anyone? You have a question?
How do you calculate the total reward of that?
We're about to talk about it. It is a little bit annoying, but we are trying to estimate it. We aren't going to calculate it. So ideally, if you're going to like win a game, it's going to be a very positive number. If you're going to lose a game, it'll be very negative, for example. But it's just some function that like we have defined and guessed. It's a little bit confusing, but we'll sort of get into the derivation for it, and hopefully it'll make more sense then. Which I think is next. Yeah. Okay. So this isn't so bad. I have actually, you know, let me, in case anyone does use the recording this time, let me stop sharing so you can see. Sweet. So we are going to try and do some sort of derivation. So help me through this. What actually is our Q function, right? It was on the previous slide. No trick questions here. If someone wouldn't mind just like shouting out what it's supposed to be doing. Maybe?
More.
It's a reward function. So it'll say it takes the state action pair, but what's it trying to predict?
Expected reward.
Yeah, it's the total reward. So we're trying to find like all future reward given we take this action, right? And one way we can think of this is we can say that this Q function is equal to the expectation of like the immediate reward we're going to get, but then we can also add in like the next reward, and then we can add in the next one, and then we can add in the next one, and we can just keep going. Go ahead.
Is this like recursive algorithm?
You are slightly ahead of me. So before we make it recursive, we have a parameter we want to add to this that's going to be in all of these equations. You'll see it everywhere. We want to add in gamma. So the idea here, this isn't like a mathematical operation that's valid. We're just going to try and say that maybe we care about rewards now a little bit more than we do rewards in the future, just so we don't like try and predict too far, because maybe predicting too far is bad. It really depends on your problem, but we'll just say that there is some parameter gamma, I don't know how to draw gamma pretty, that accumulates over time where you get something like this. So you have like gamma R1, so gamma might be a number between like 0 and 1, right? And you multiply, like next one is squared, and the next one will be cubed, and so on. Okay, now we can actually do some math operations on this to do something useful. We can use the linearity of expectation to first say that the expectation of this is equal to the expectation of our immediate reward, then plus, yeah, exactly, the expectation of the rest, right? Which here is going to be gamma R1, and then gamma squared R2, and so on. And then here we have something a little bit neat. Does anyone have any guesses what we can do next with this? How we might simplify this maybe? Pause and ponder for a moment. It's actually somewhat clever, and it's annoying when you see it, I think. You have an idea?
Like factor out the gamma.
Factor out a gamma. That's a good start. Let's do that. So we end up with the expectation of our immediate reward, just like before, plus some gamma times the expected value of R1, and then exactly gamma R2, and so on. And this is,
You know, linear, so you could just like stream the operation, the expected value operation.
expected value operation to each. Oh, you could. Since it's linear, that's how we were able to take out the gamma. But even more pretty than that, what we should try and do, instead of thinking about this right now, what if we think a little bit more here? Does anyone see what we can do here? Have an idea? All right. It's actually it's annoyingly clever. We can just say that we have this is equal to the expectation of our immediate reward, right? Plus our Q function for some like next state. Right? Because this, or sorry, gamma times that state. I almost missed that. That would have been embarrassing. Just running a little bit low on space here. My font got smaller as we go down. So the idea here is that since we want to take the expectation of the total reward, all we want to do is take like, the total reward. We're going to add some gamma factor because we want to discount future rewards. But then we can use linearity of expectation to define this as like a recursive function. And the beauty here is that we just need the immediate reward, and then we can just use our guess again in our new state. But this is a little bit weird because we don't know what our next action is, right? Because like A prime, what is A prime? So we do have to add one more thing to get us to what's called the Bellman equation. What we want is to actually take the maximum of our next states, right? Because we want at every single time, we're trying to predict the next best action, right? We're always going to do like an argmax. So what we can do is we can say that this whole expectation value, just like before, is the expected reward. So reward 0. And then we can add in our gamma term. and then max of like A prime, we'll say like in our action space of our new state, and then our action. So this becomes our Bellman equation. You'll see this unfortunately everywhere. I say unfortunately, but like the Bellman equation is how value iteration was able to propagate backwards because it has this term, right? This term helps you propagate like future values back into like current values. And this is how Q learning is going to learn. So trying to think about this intuitively, we're trying to create some function Q that's able to predict the total reward. And it does that by predicting the current expected reward of the immediate move, and then adding in some future reward as well. So this is somewhat abstract, and I think I lost at least some of you here. So before I keep going, does anyone want to ask questions about this? Do you have an idea or question?
Yeah, a question. Isn't it just saying we add in the reward for the current I believe action, right?
Yeah.
And then we figure out what the next best action is and we calculate the reward.
Pretty much.
That's what it's like.
Yeah, but the beauty is our learned function, we aren't going to actually have to like go in and loop through it. It's just going to try and learn this value. So we don't actually like in code have to go like for each action. It's going to just try and learn what this value is.
Learn the function Q or about specific.
Our Q function is going to try and learn the recursive behavior without us explicitly doing recursion. Because like right now, this is recursion, right? Like if you wanted to do this perfectly in code, you would have to call Q, which would call Q, which would call Q, and we run into an issue here, right? So the point of the Bellman equation and what we're trying to estimate is that we don't actually have to call Q again. We're just trying to do like the expectation of Q here, right? I would fit it in, but I can't. We actually just want to predict what the Q probably is. So for example, in our maze where only one tile had a positive reward, the Q, like this is only ever going to return, this is only ever going to increment when we get like close to the end state, right? And then that's going to propagate back as we like explore.
Could you like set a base case to be like when your move results in you winning?
A base case of when you,
For like the maze, for example, if you get to the end of the maze, wouldn't that be like the base case? And could you implement the recursive?
I think that's closer to value iteration. I think what you're trying to get at is like if we have all this information, why don't we just like start where we're winning and like spread out, right?
Yeah, because like I guess like if you would call Q again, then doing the same thing until you get to only like one possible move to get into the.
Notably, we aren't calling Q again. We're trying to estimate what it is going to be. So like if I get rid of this, right? Right now, we've done the derivation. We don't care anymore. Actually, I still want this. To be a little bit more clear, we are trying to estimate our next Q value. So we're trying to take the expectation of max A prime in our action space. So we're trying to find the best action of our Q from our new state and our best action. So we aren't actually recursively calling Q, right? We are just trying to estimate what this value might be, which is weird because like if you've taken statistics, I personally don't know how expectation works on max. It's probably not that hard to derive, but like this is confusing. How do you do expectation on a max from a list on some function? Is this function even linear, right? We run into some issues here where it's hard to do our predictions. All we want to do is try to estimate this value. And our Q function, since it's estimating this whole value, it ends up being recursive like implicitly, even though we aren't actually doing recursive calls in code. Okay, so I have like 30% of people looking at me confused, 30% with like blank stares, and then 30% like, yeah, this makes sense. So you have a question?
What is gamma? Like, does it represent anything, or is it just some random constant?
Gamma is like a hyperparameter. It's one that you choose as the developer. Generally speaking, like if you don't care at all about the future, you would just set gamma to be 0, right? Because then it doesn't become recursive. You don't care about the future. You probably shouldn't do this because this isn't, if we're trying to do Q learning, the whole point is that we have this gamma be more than 0.
What could the max value for gamma be?
Well, that's interesting point. So if I still have this like gamma plus gamma squared, we run into a calculus problem of it's a geometric series. So if you have gamma plus gamma squared plus gamma whatever and so on, you can't have gamma be equal or greater. I'm pretty sure it's greater than or equal to 1 because then it diverges. Yeah, of course, if it's 1, it diverges. This would be a geometric series, right? You could probably have it be equal to 1 in neural networks, and it might be fine sometimes, but you're probably going to get stability issues, and it might diverge. So in order to avoid that divergence, you should probably keep it like 0.999 at the most.
Why do we discount future reward? Like, wouldn't it all, are we saying that it's like, it's valued less?
So if you're in like a world with no probabilities, it's probably a good idea to not discount future rewards or discount them like very little, because you sort of know how the future is going to play out like perfectly. You sort of have this like model, even though you don't have the model technically because this is a modelless function. But if it's a very probabilistic world, right, you don't know what your actions are really going to do, then you probably shouldn't be trying to predict the future so much. So we use our gamma factor to avoid trying to predict the future too hard when we really don't know what the future is going to be. Right? Like in real life, if you're trying to make the most money, if you're like a college student, maybe that means that you're picking like, I'm going to be a finance major. But you probably shouldn't plan out your like next job as well after finance major. Or maybe you do, but like you shouldn't plan out too far ahead because life is complicated. So you could sort of say that this gamma factor is a way of saying life is complicated. We keep it relatively low because life is complicated, or if life is simple, then we keep it high.
Then why don't we just look at just like the first, like the next couple moves after the current? Like, why are we looking at all of next possible?
Well, it's just an approximation, so we're not actually looking at all possible moves. Eventually, this gamma factor will approach 0. So we're not really looking to infinity, but conceptually, we kind of are. It's sort of the conceptual experience of like planning ahead. You have a question or?
Would it be possible to like do this in a way where you're not estimating and actually like kind of do recursively, like test every single option kind of?
Yeah, you could. That wouldn't be Q learning. You can definitely. It's possible. It wouldn't be Q learning, and it would be a very different problem. It might not be the best solution to your problem, or maybe it is better than Q learning in your case. It depends. If you have like the exact answer to this equation, you probably have a simple model. So like your P and your R are probably like there and available to you. So you just do like value iteration. So if you have like a perfect Q and it's easy, you would probably do value iteration. And I think that's closest to what you're describing. Go ahead.
So you learning, I mean, just quick question.
Yeah.
It's easy to pick the most optimal action if you know the total reward for each action, but Q learning is about, I mean, I guess that second term in the expression about like learning to predict the future or like making a map of like state action pairs to total reward. So it's about like learning to like predict the future, right? And predict rewards in the future. That's what Q learning is.
Yeah, one of the hard problems in Q learning or in like machine learning in general is like sparsity. So sometimes I take an action, but like if my goal right now is to make mac and cheese, I don't know why I keep going to that example, it's terrible, but if I take this step, is it clear that I did better? Like, did I get a reward for making mac and cheese by taking this step? Probably not, but maybe that way is the kitchen. So maybe I should be rewarded in some way. So the idea behind this Bellman equation is that it's sort of taking that future into account, where getting like closer to the kitchen is a good idea if you want to make mac and cheese. I hate this example. I should have come up with good examples before I came here, but conceptually, you're trying to predict like your immediate future reward, but since your immediate future reward might not be very, like this might be very good, but deceptively, you might not do well in the future. So we are trying to seek the solution to this problem where rewards can change over time, and maybe you have like sparse graphs where it's like you don't know when you get a reward. This sort of seeks to solve that. Go ahead.
Just curious, I remember in like the first video you showed like the demo of what's it called?
Doodle jump?
Yeah, this is how that was thinking.
Yes.
So was it,
Very
like,
poorly though.
we're taking like every frame and like the current state and then like guessing it's going
Sort of. I'm going to make you ask that question again later, or if you feel it answered by the slides later, that's good too. Basically, we could take an image and try and put it through neural network. We did a simpler approach. Or I did a simpler approach. Okay, any more questions here, or? Okay, hopefully I've justified like why that equation is cool, and hopefully that you know why we want to use it. So I think I just go through that again on the slides here. Here, let me turn the screen back on in case anyone watches this later. Share. Sweet. Whatever. So our Q function, as I say in the slides, is just our immediate reward plus the expected future. The technical term there is bootstrapping, but don't worry so much about that one. And then one of the things that I mentioned here is that we can adjust our Q function over time. There's many ways to do this. Maybe we do a neural network. In our first example, we're going to look at a grid. So you can measure the actual reward after you take that best action. And if that actual reward does not match up with your predicted reward, then you can make changes. And over time, those changes also like take into account the future, because you do that for every state, not just your current state, right? Because you explore for a long time. Okay, so the first example of Q-learning is in the grid world. And I think it's cool to look at the Karpathy diagram again, because I'm going to pull that up and we'll see how it explores. But in this example, we can imagine that instead of having a neural network to learn, we have just like this grid of weights. So in this grid, like each action has an associated weight with it, and we want the most positive weights. So I believe next, so same grid problem. We're just, I'm going to go back to that. Same grid problem, but now we want to go into the TD one, which I think we're already in. Yep. So now, when I start this, you're going to see it's doing something weird. Since we don't have access to the world model, we can't simulate yet, right? And right now, our weights are either like randomly initialized, or in this case, 0. So it has no idea what it's doing, right? It's just sort of basically guessing. And over time, it's going to be exploring this maze. And eventually, you'll see it find some path that it likes. And we're still sort of exploring randomly sometimes because of how Q-learning works. I'll talk about that more later. But eventually, it learns what a good path is, and it takes it. So although this took a long time, right? Now we have found a path that's pretty optimal, and it's going to take that almost every time. So this is like exploiting now the information it got. So very generally, Q-learning is this process of exploring to update our Bellman equation. And then we're going to then use that Bellman equation after we've trained it to exploit it and take the optimal path. All right, so if I go back, let me actually go back to the code. I went through and colored everything. This took me a while. All right, so you can think of, if you prefer the code samples, and I know you told me that you don't like them, but I did it anyway. You can imagine that you first initialize your table with just like a bunch of zeros. And whenever you want to pick an action, you're literally just picking the best action at your current state. Right? So you loop through every action that you currently have available to you, and then you pick the best one. So then you can update afterwards. And this is just a way of measuring like your change. And depending on how much time we have, we can talk about that change a little bit more. But I think I've actually taken up a good bit of time already. Yeah. So I'll go back to that if we're curious, but I want to talk about neural networks real quickly because that's what you're here for, probably. So in our grid world, it's like kind of nice because it works. But Snake, for example, our reward changes, which immediately makes that grid world example not very good. Because how do we change the grid? There's probably a way to do it, but it's going to be sufficiently complicated. And I'm just going to say that there's a better way to handle that. Let's instead try and consider the neural network approach, right? So here I'm just justifying that the constant, like these apples change positions. So our grid sucks after we eat one apple. So I created ASCII art because I couldn't be bothered to generate anything better. And the very rough idea here is that we want to decompose our state into some useful set of variables, right? So you can think of S, right, our current state as a vector, and it has these properties. And we'll talk about this in a second. But then we feed this into some hidden layer or many hidden layers, and then we output Q values. So in the case of Snake, for example, you might just output the expected reward if you go up or down or left or right. And we don't have to do too much here. We can just like hope that the neural network will learn, right? This is sort of the ML approach. But before I go to the next slide, does anyone have any idea of like what we might put in for these X values? Does anyone want to take a stab at what we could put in? There's like really no wrong answers here. We could do a million things, but just to drive a point home, maybe. Does anyone want to take a guess? You want to try?
Maybe like the distance from an apple.
Yeah, you could take the distance, like horizontal and vertical, to an apple. That'd be really good because then the snake knows which direction to go in. You have an idea?
A really robust approach would be like map every single square to like about like one of those entries and then input like a 0, 0.5, or 1, depending on what's in that square.
So input like the whole board.
Yeah, exactly.
And everything's going to be 0 except for where the apples are.
Sure.
Yeah, that's probably good. In addition to that, you probably want to encode your current snake location.
Like -1 or something.
Right. You could do that. That would work. That's a complicated way to do it, but it would still work. I say complicated just because there'd be a lot of inputs. Does anyone want to try other information we could put in? You have an idea? Walls. Yeah, that would probably be pretty important. If we can move in a given direction, otherwise we would just crash into a wall and die. That's not so good in Snake. Yeah, so the approach I put onto the ASCII art is that you might want to have like your current location, where food is, maybe if you can move up or down, what your current direction looks like. There's a million different ways to encode this. This would not be my preferred way of Snake. I would probably put things as like relative coordinates instead of like absolute x, y. There's a million changes you could do here. Like the image approach is really strong. This is just one idea. And then I finally talk about the exploration bit of Q-learning. So if we have this neural network, right, we have to train it somehow, which means we have to get data. And that's kind of annoying because we can't model out the world, right? We don't have any way to predict the future. So instead, we just have to play our games, right? We have to play games over and over again. And we have two things. We have exploration and exploitation. So the idea behind exploration is that sometimes you pick a random action. So instead of picking your max action, you pick a random one. The rough idea here is that if I'm going to get mac and cheese, maybe I find that I can go through this door to get towards the kitchen. And that's great. But if the kitchen's that way, this is not so ideal. So maybe I should sometimes randomly pick an action. And maybe I end up in this action that I haven't seen before. And that causes me to move towards that door. And then I find that that door's better. So the idea is we're sometimes using our Bellman equation to pick the best action, but sometimes we're choosing randomly, right? And then, sorry, go ahead.
So is the exploration version like very exhaustive?
It takes time because in order for you to train on a game, you basically have to explore the game. You basically have to play the whole game over and over again. Yeah, it's fairly brute force. So if you're playing a simple game like Snake, there's better ways. But if you're playing a really complicated game like life, maybe not so much. But as we play our games, we can save this like tuple of information. So we can save the current state and the action we took, and then the actual reward we got by moving. So like if I move this way towards the kitchen, I would get the reward, right? Because this is good. And then our next state. So we can store all this information in order to then train later, right? We one by one feed this into our neural network, and then we run gradient descent, just like how we talked about before with backpropagation, just everything else. We just have one big thing of data that we accumulate over time. There's a bunch of ways to handle this. You could like have a fixed buffer size that you throw out old values from once you've seen too many new values. There's all kinds of like replacement options you can do. This is sort of just like machine learning heavy stuff that you'll get into. I didn't want to go too deep into that now because we're going to probably be doing this next week of like actually playing games, ideally. So very roughly, we're just going to save the data and then we're going to train on it. And next time we'll see how that works. But if we've done the backpropagation before, hopefully you can take a guess at how that works. But I believe this is all I had. Oh, I had useful words, if you like the useful words. But this is sort of all I have right now. I could do the learning bit, but I think I've used up a good bit of time already, so I'm probably not going to do that right now. If you're interested, you can talk to me after. So next time, we're going to be talking about Q-learning still, but we're going to try and implement it into Snake first. So hopefully, we will be able to take our Bellman equation and learn it for Snake. And then we'll find some way to use a neural network to learn it. So you have any? If you've done the previous, like PyTorch, as long as you have like Python and whatnot, you're good. I'll have a GitHub repository for Snake that you'll just clone. So does anyone have any questions about this or next meeting or anything? All right, well then that's all I got for you right now. Hopefully you got Q-learning. See you guys next time.
I have a question. So this is like kind of discrete actions. What if we have a continuous action?
We still can do it. Like,
Like,
in the case of me walking,
yeah.
so like you'd say it like this is an action and this and this and this. So it's like very continuous.
All like discrete.
You'd probably want to discretize it somehow with maybe like fixed time steps. So if I took some action to like go right, you'd probably measure it like 0.1 seconds later. And if I, and then you'd measure the state there, see what the reward was, et cetera. You'd probably find some way to discretize it because like in a computer, it's not continuous, right?
Yeah.
It's like limited by frame rate of a camera, for example. Yeah, question?
That's nature. The like you just might go through the entire path. That's assumed to be just or yeah.
So initially, we don't have any useful way of knowing what our function is going to be, right? If I go to the example again,
It's like being it's hard to. We should probably it's like map major.
so like here, we really have no idea what's going on. And you might see that there's like a little trick involved here where we are making these weights negative. That's just like an optimization we might do to discourage us from looping around the same area all over. But the rough idea is we have no idea what to do initially. So our Bellman equation is like 0 or it sucks. That's the best way to say it. It's terrible. It doesn't estimate anything useful. So over time, we just explore randomly. And eventually we get to like here. And then we realize, oh, there's a huge reward here. So then we train all of our previous saved functions, right? Because we saved everything in a huge buffer. And this sort of like back propagates, right? So the back propagation is the way to change like all of our previous states. So we sort of fill in information over time. There's a bunch of inherited issues. I'm surprised I haven't run into it already. Like maybe we end up finding that this path is a good path, and then we get stuck there. Like that can happen.
Yeah, what are you trying to do though? What's that? It's actually.
In this maze, there's a reward here. And whenever you get to this reward, you reset. So you get like the +1. So our,
And like I never realized you could just go straight down instead of going all the way around.
oh, it could, it easily could. Since we explore randomly, it might actually do that first. Ideally, we find a way to avoid that. So there's a bunch of tricks you can apply in Q-learning, like you can assign weights that are negative if you want to long paths, like you can decrement things over time. It very much depends. Ideally, we don't have such a sparse reward function, right? So instead of having like 1 here, we might also have a 1 here. So we know that, so it's much more likely that we find this point first, right? And that way we then have more chance of finding this point and find the actual shortest path. But
Why don't we just implement this like actually explicitly like recursively? Because wouldn't the base
That
case
only works. That only works when we have the whole model, right? So you in here it's easy, right? And I showed you the value iteration. You don't always have that info. So like here, of course you do, but
So that's the great reward is, or
take Pac-Man as a sample. There's rewards everywhere. And then there's also punishments everywhere. I say everywhere, it's like the ghosts. It's not entirely clear what like the best path is. So some people who took 440 recently have found out that it's probably really hard to calculate what like the best path is throughout a whole maze to find all of the pellets in the shortest time. And then this becomes much harder when you have the ghosts. So if anyone in 440 wants to talk about how it takes minutes, some of their solutions took 20 minutes to find like 10 pellets. This becomes really hard.
There's more things that are
Right. Once things become dynamic, like once they move around, it becomes harder. Once you have many rewards instead of 1, it becomes harder. Once you have like rewards that change, right? Because like pellets in the Pac-Man maze get removed over time, it becomes much harder. So the very rough idea is that we would love to actually recursively do this, but we can't because it's too complicated.
So if we had like better computers, couldn't we just do that instead then?
Yeah. Yeah, I mean, if like Pac-Man in particular is probably also simple enough to solve using an algorithm. I say solve, but play using an algorithm that's simpler than Q-learning. But the idea is that like Boston Dynamics, for example, makes robots. They probably don't just use predefined functions and if statements. They probably have a lot of dynamic programming. I say probably, they definitely do. They're not stupid. They're doing this for a reason. Even though they have a lot of compute, it's way too hard. So eventually you just come into a problem that's way too hard to functionally solve. You have to estimate the solution instead. So it's all about estimations. Yeah.
What if you start the agent at different parts of the map? Wouldn't that allow it to like make the best sort of representation of?
That's a good idea. Yeah, if you want it to understand the entire state space instead of just its like local area, you should do that. That would be a good way to train. You should do that in like Pac-Man, for example, because that helps you generalize more instead of fine tuning onto one and then overfitting. So yes, you do want to do that. Yeah. These were good questions.
In this example, like the starting point is always like when you're actually playing the game and trying to win it, you're always starting from the top left.
Yeah, in this particular simple game, eating the pellet, for example, just brings you to top left.
Just kind of like a slope field, right?
Sorry, a smoke field?
Like a slope field is kind of like
Yeah.
going.
There's like one local minimum, or if you want to think of it that way, it's
No.
I don't entirely like it.
It's like if you drop a marble in that spot and like it follows, like based on the vectors and their magnitude, it follows where.
In that sense, I like that. But it's this is not modeling a slope field. This is not modeling a continuous equation. This is modeling like a list of actions. It's trying to estimate which actions you should take. So it doesn't really translate perfectly to a ball rolling down a hill, but it's like approximately there.
You can't say that those arrows are the gradient.
It's definitely not the gradient. Or it's definitely not the gradient if you're talking in terms of our like parameters.
If you just have like a function for like reward, like if you follow like the quickest path, right? That's what we're trying to do, right? Kind of get the quickest path to the reward.
In this case, we're actually just trying to find a path technically. We probably want it to be the quickest path, but yes.
So you determine like if it's the quickest path based on the gamma value, right? So figure out how much you weight the feature.
Our reward function in particular here is just give you 1 if you hit the end. So if we wanted it to be the actual shortest path, we would do things like give you 1 if we're at the end, but also give you like minus 0.005 if you're not at the end. Because that way, if you take an action that takes you further away from the end goal, it'll penalize you. So that would be trying to find the shortest one. So your actual reward function, right? Not the predicted one, the actual reward right here is a function that you define, and that's the problem you define, right? So if you want it to be the shortest path, you would do that, right? So +1 if you hit the end goal, minus some small number if you aren't at the end.
You're going to think about it, or?
You do have to think about it.
Thank you.
Have a good one.
If your real reward function here is just giving you a reward of 1 at the end, why is the maximum reward there 1.2?
So this is the grid approach. I don't know Kaparthi's code. I don't know what he wrote here. It's possible that he had his learning rate go down, and so maybe his learning rate was really high initially, and it like jumped over, and then he brought his learning rate down, so it never really settled to the correct value. I didn't actually check the code for this, though.
It confused me the whole time I was staring at it. And I was like, what is? Because even if you jump over, if you're just applying the Bellman operator a bunch of times for the first example, you should never overestimate your Q values if you start at 0.
You shouldn't. You shouldn't be doing it. I think it's interesting in this case because it's also not a probabilistic world. So your learning rate should be able to like handle it. It overestimating is probably not good, but I was using this diagram more as a visual because there aren't very many good Q learning visuals.